All right, now that we've introduced the electric field and electric field lines, we need to introduce something called electric flux, or the idea of flux. This is going to allow us to use something known as Gauss's law that we'll introduce in the next class. All right, so first, let's define this idea of flux as a measure of how much of something passes through a given area. And so my sort of everyday example of flux would be like if you take a bucket out into the rain, you can essentially get a measure of the rain flux that's passing through the bucket opening. And so that depends on not only how much rain is falling, but also the size of your bucket. And then the other thing that it depends on is the orientation of the bucket opening relative to the direction that the rain is falling. And so the orientation between the direction of the electric field that we're going to talk about, the orientation between that vector and the direction in which you'd pass through the area of your interested surface, that direction matters. So this is really what we mean when we talk about electric flux. It's a measure of how much of the field here is passing through this surface, through this area. And again, the electric flux is going to depend on the field itself, but then also the area. And we actually have a way to define an area vector. And so the area vector, if you look down here, the area vector is really just the area of a surface, but it takes into account the direction that's perpendicular to that surface. And so when we have things called open surfaces, like these two sheets here, there's actually an ambiguity. You could say that the direction, the area vector, is pointing up, like in this case, or you could say it's pointing down. Over here, there's just another example of the same thing. And now this one, this is actually a closed surface. And so this is, well, it looks like a light bulb, but be similar to a sphere. And when you have a closed surface, the area vector, or this normal vector, so these vectors that point perpendicular to the surface, they are defined as pointing from inside to outside, so passing through the surface. And so with a closed surface, you don't have the ambiguity that you have with the open surface. Now, for electric flux, if the electric field is uniform and our surface is flat, so here I've got some electric field lines drawn, and I've got 4 different surfaces that I've drawn. And the first 3 we're sort of viewing edge on, whereas this last one has been rotated so we can actually see the full area. And the area vector that we just talked about, remember, perpendicular to the area. So in those first 3 cases, the area vector is sort of changing direction as the surface changes orientation. And then over here, the area vector is actually pointing into or out of the page. And so it's a little difficult to represent it. And so the electric flux, if the E field is uniform and the surface is flat, the electric flux is just the dot product between the electric field vector and the area vector. Now, if the E field's not uniform, or if the surface isn't flat, then what you have to do is break up the surface into small chunks and essentially do an integral of the dot product between E and the infinitesimal surface area element. And if our surface is closed, then the integration symbol just takes on this closed notation, letting us know that we're integrating over the entire surface. All right, so now we're going to continue in class with a few examples where we're going to calculate the electric flux, and that'll get us ready to use Gauss's law in the next class.